Okay, so everything should be the same as the previous lecture. So I'll just go and, I mean, usually the screen is over here, but.
I'm not sure that right.
Okay, okay, so I'll just start because it's already 5 minutes.
Yeah.
So, okay, all right, thank you. All right, guys, hi. Sorry for the little delay for technical difficulties, but we're ready to start. My name is Rai Sakur, and I'm the last in list of the instructors that you'll have for this course this semester. So today we'll be talking about neural models of language. Before I get started, I wanted to quickly recap some of the course logistics. Assignment 1 is due next Friday, and assignment 2 will be released right the day after. There will be no lectures during the reading week break, and final exam, whether you're a grad student or undergrad, you'll have to write it. And please use the URL here to provide any anonymous feedback or thoughts you have in order to, for us to improve the lecture. That's very much appreciated. So a quick lecture plan for today and the next couple of weeks. So today I'll be introducing neural models of language, then word level representations like skipgram and continuous bag of words. Then we'll look at some pedagogical neural language models and training, and then we'll move on to more standard architectures like RNNs and LSTMs. In the next lecture, we'll be doing machine translation, and in the process, we'll be looking at SIG-to-SIG models with attention and transformers. And we'll have a session to talk more about large language models and foundation models like BERT and GPTs and some implications that you should be aware of as CS students. Okay, so artificial neural networks are inspired from neurobiology. Each unit has many inputs called dendrites and one output called axon. The nucleus fires or sends an electric signal along the axon, and the learning happens at the synapses that connect the neurons. The artificial counterpart of a perceptron is called, neuron is a perceptron. So essentially the idea is very similar. You have activation signals coming from connected neurons, and in the nucleus or the center, you're doing a weighted average, and then passing it through an activation function denoted by G over here, which essentially acts as a filter function to allow the signal through if it's high enough, if it's above the threshold. If not, it just doesn't allow it to pass. Okay, so the perceptron output is determined by activation functions, which can be nonlinear functions of the weighted input. That's why it's also called sometimes nonlinearities. Most popular activation functions are hyperbolic tan and the sigmoid function. The idea or the intuition behind activation function is to think about that they suppress or constrain the output within some range, and they're easy to take derivatives on. So on the bottom left, you have a picture of the hyperbolic tan, and the output over here, good. The output is constrained between -1 and 1, whereas on the right-hand side, you have the sigmoid where the output is between 0 and 1. And over here, you have the equation for activation for a sigmoid function. And as you can see that the sigmoid function, the derivative is easily computable. And we'll talk about why derivatives are important in a second. Okay. Since 2011, rectified linear units, or ReLU, has become the most popular and maybe the de facto choice for deep learning architecture as the activation function. The reason is because it has a few very attractive properties like sparse activation, limiting the vanishing gradient problem, and most importantly, it's very efficient to compute. On the bottom, you can see the blue line over here. This is the activation function curve for a ReLU. And the ReLU has many different variants. One example is shown over here in the green line, which is a soft plus function, which is a soft, smooth approximation of the ReLU. And it also has the property of a very simple derivative. So why do we care about derivatives? We care about the derivatives because the learning in perceptron happens using a gradient descent, which is an iterative gradient ascent or descent algorithm, which iteratively updates the weights of a perceptron. The way it happens is that you calculate the error. So you have a ground truth and you have a model output, and essentially you calculate the error, and then you backpropagate the amount of error through your network, and the activation function derivatives allows us to take a step towards the steepest gradient direction. And the steepest gradient direction gives us the direction which will reduce the error the most at any step. Let's talk about some limitations of simple perceptron. So a simple perceptron is unable to learn anything that cannot be linearly separable. So in the figures below, the first two, this is like, the AND and OR function it can learn, but if we give it a XOR function, it's unable to learn this simple function, because if you can see in the figure, there's no way we can draw one line to separate this, the black nodes and the white nodes. So this simple failure, as a historical note, was noted in a paper by Minsky and Papert in 1969. And that was followed by this report called Lytle report. And if you're interested in AI history, it's included in the course website as a supplementary reading. So once the Lytle report came out in 1973, this sort of marginalized like AI research, neural network-based AI research for about a decade, and what is now known as the first AI winter in AI research. However, as it turns out that perceptrons can be used to represent complex functions, and Minsky and Papert were aware of this, but at that time, the concept of using multi-layer perceptron or layers of perceptron was computationally so infeasible or implausible that it never became a mainstream thing. So if we layer up the perceptrons and what's called a multi-layer perceptron, then it is able to represent any complex function. And the way it happens is that you pass the inputs at the bottom layer, you're passing the inputs in orange. It goes through some hidden layers, and then as the output, you have the green layer as the output layer, which usually gives you the probability of, or whatever your objective function is. And they're quite robust to noise, and they're trained specifically to reduce error. So as an example, like think of if you have a whole bunch of images and you're trying to classify these images into some object category, the way you do it is that you'll take an image and then rasterize it or get the pixelized form, and you'll pass the pixels in your input layers, and it will go through this hidden layers of perceptrons, and in the output layer, you'd have the object category or classification probability. So for example, in this case, you could have like dogs, cats, or some other animals, and the output, like after train, the probability for cats for this picture would be the maximum, and you can classify this using that. So it's basically a multinomial distribution over animal categories. Similarly, you can train on human faces and classify their emotional state. So it could be something like you take this picture, and then it comes out as like this person is depressed. Okay, so we can do this using image, but how do you do this for words? So in order for us to use it in language, we need to represent the words in some form. And this is where the part of like word representation comes in. So the classical approach, or the easiest approach, or the simplest approach, is to simply take a word and given a vocabulary of certain size, we just use an index value as the representation. And this is known as the so-called one-hot representation or one-hot encoding. So here you have the word lugubrious, and you just assign the value 1 to one of the indexes in your vocabulary. And if you have done assignment 1, you may have already seen that we can similarly assign word features to any word, like feature representation to any word in a more dense or floating point numbers. For example, like we can assign psychology-based features like cheerful or emotional tone or age of accusation and things like that. So you'd have, let's say, this column over here denotes cheerful, or this column over here denotes emotional tone, whatever it is, but you can assign it, and you have seen this assignment 1. And now the question is that how do we learn such dense representation? You have been using these features in your assignment 1 to assign to words, but how did that feature value come from? How did we learn that? So you shall know a word by the company it keeps. It's a very famous saying from the researcher J.R. Firth in 1957. And modern word representations are inspired by this saying. So essentially, in 2039, Mikolov et al. Proposed word-to-vec techniques, which includes the continuous bag of words and skipgram models. And what it is that you're given a context window, you're trying to predict the center word given the surrounding words. So that is the center of words model, and we'll look into how it works next. So for the sake of simplicity, let's use this two sentence as our running example. So been feeling lugubrious all day, and we have another window that says felt lugubrious sadness in. Okay, so we will be trying to predict the center word, which is lugubrious. And to keep things simple, let's just use a window size of like 2 for now, which means you'll have an input word and an output word. With that in mind, let's go over here. So this is a high-level diagram of the continuous bag of words model. So remember that this is just one word in context. So essentially, for words feeling lugubrious, you have a one-hot encoding of feeling, which is X, and it has dimension of D, which is the size of the vocabulary. So it just has, and then you have a matrix called the embedding matrix, WI over here, of dimension D into H. And this, you get a vector input vector embedding, VW, by multiplying X with the embedding vector, input embedding vector. So for example, like if you have, can someone tell me what would be the dimension of VW over here? So VW equals to X transpose times embedding vector. So VW is, what's the dimension for VW in this case? So it will be just like H, right? So you get, so on the right-hand side, you can see how VW, like in blue over here, is the input word embedding, which is obtained by multiplying X transpose with the embedding word. And this is essentially like this Wth row of this embedding matrix. And this is of dimension H. Any questions? Okay, similarly for the output word, we have embedding matrix, which we denote by WO, and Y is again a d-dimensional vector. Y shows that what is the output word, and basically if it's lugubrious, then Y would have a 1 in the position of index of lugubrious. So that is the idea, and what we're trying to learn over here. So since it's just input two-word context window, so we're just trying to maximize this probability here. Given input word, this is the output word we're looking for. So we're trying to maximize this probability, which is denoted, this is the softmax function for a bigrams, like a probability of output word given input word. Okay, so we'll be trying to maximize this. So what happens if it is like multiple contexts? Like so far we just looked at feeling lugubrious, but now we're saying that, okay, so the context is of like, let's say if it's 4 words, so then you're given been feeling all, and we're trying to predict lugubrious. So everything remains the same. The only thing is that now we add an intermediate layer, which takes, so each of the input words, you'll have an input embedding, and then you have an ever intermediate layer that takes this other, C value, other words, and then averages it, and then everything else remains the same. So the only thing is that we're injecting an intermediate layer that averages all the other words in the context, but otherwise everything else is the same. Now, skipgrams is the other word-to-vec representation technique that was proposed, and essentially this is an inversion of the tasks. So it's identical to continuous bag of words, but here we invert the task, meaning that we predict the context words given the center word or the current word. So on the right-hand side, you can see the architecture. You're given some word, let's call it the center or current word, and then you're trying to predict what are the context words. So instead of having one multinomial distribution for here, you're going to have C multinomial distribution for the C words. Any questions? Okay. Okay, so that's fine. So now let's talk about how the learning is happening, how we're updating this weight. So in order to talk about learning, we need to talk about what are our model parameters. So our model parameters in this case are the word embeddings of the input words and the output words. So we have V input words, and we have V output word embeddings. So the bottom greens are input word embeddings, and the top greens are input word embeddings, and the bottom blue are output word embeddings. And the total size of our parameter matrix is 2V into H. So we'll be using gradient descent to do the learning. If we're given a T token of training data, so we're trying to optimize this objective function over here, which is essentially, again, we're trying to optimize given input word, the output word. So we have a training corpus or training data. So each input token T, this should be the output word. So we have samples for this, and this is what we're trying to optimize. In order to optimize, we have to take the derivative of the log of the softmax function. Why? Because the probability of the output word given the input word is given by this softmax function form over here, and we have to take, in order to do a gradient descent, we need to take the derivative of this function over here, and then use that derivative to update using stochastic gradient descent like this, like old parameters updated by the gradient direction, by the gradient that we're going to take. So let's look at how we can take the gradient. Please raise your hands if you have any question. I'm happy to explain things if it's not clear. So here we're taking the log derivative of the log of probability of the output word given the input word. And here, this is the softmax function expression. And log division becomes subtraction. So on the left-hand side, we have the numerator. And on the right-hand side, we have the denominator. On the left-hand side, and this derivative operator goes inside the bracket. This log and exp terms cancel, and it's just the derivative of the output word embedding with respect to the input word embedding. So the left-hand side just becomes this. On the right-hand side, you're taking a derivative of log sum exp, this guy over here. And if you, so this, if you apply the chain rule, then you have to convince yourself that this in the red rectangle simplifies to this guy over here. So it's basically like you take the derivative of, if you have any, this should be a homework, a very basic homework for you to convince yourself. If you don't see this, please see me after the class and we can do this over the board. But all right. So now, why do we need to get the vector embeddings? So why do we need VW, or why we're doing this multiplication? Why are we multiplying the one-hot encoding with the input embedding matrix? So the reason is that, like, if it's one-hot encoding, then we can't really capture the semantic similarity between two words. So, for example, using one-hot encoding, you have the two encodings of the words lugubrious and sad. And if you apply the cosine similarity function, which is on the bottom right for your refreshing your memory, this just becomes 0, right? So so we want to be able, so this doesn't capture any semantic similarity, although lugubrious and sad are semantically similar words. But once you take the embedding, you get a dense form of representation in floating point numbers. And in the latent space, once you repeat the cosine similarity function, you see that it gives us 0.9, which is right because lugubrious and sad are related words, so they should have a high similarity measure. So now, what we described is very inefficient if you think about it. What we're trying to do is that we're taking each input word and we're matching it up against all the 100K words in our vocabulary. And if you have to do that, you can see that it's computationally infeasible. If you look at the bottom expression, the mathematical expression, the softmax function, this bottom part over here is computationally infeasible because you have VC and you're trying to compare it against all the W's in the vocab, which is computationally impossible, or not impossible, infeasible. So how can we improve this? So all we want to do here is that we want to, for the true pairs, like lugubrious and sad, we want to maximize or increase the probability, and we want to decrease the probability of irrelevant connections. So for example, lugubrious does not have anything to do with zebra or clock or table, right? So we want to, basically that's all we need to do. So is there any way we can simplify this denominator over here? Instead of going through all the D words in the vocabulary, we can instead basically maybe just use a few samples. And that's what skipgram with negative sampling is. So as I said, that we want to maximize the association of words that are related. And we want to minimize the association of what it's called hallucinated context, like which does not have any relationship, like with lugubrious with roof or lugubrious with truth. So the way we do this is by choosing a small number, k, of negative words. And we just update the weights for the positive word and the k negative words. K usually in practice is between 5 to 20. And if you consider a vocabulary size of 100K, this number is only like, we only have to update less than 0.01% of our data pairs. This over here shows the objective function for skipgrams with negative sampling. So the intuition here is that you're trying to maximize the true pair, and then you're sampling, actually there's a typo here, there should be J. You're sampling like k words, and you're basically decreasing the probability of these negative samples with the input word. And this, you can ask the question that, okay, so how do we choose these k samples? The simplest thing could be to just have corpus distribution, and you just do like k random samples. We're done. That's what we're doing over here. But there are obviously variants to it. As in one paper by Thompson et al. In 2017, they choose the top k words using a modified version of it, where basically if CW is your corpus probability, they raise it to the power of 3/4. And so the intuition here is that 1/4 of the time, just pick some words that is outside the top k words. So this increases sampling of rare words or unseen words or unique words. But essentially, the end goal is the same, that we want to use those deassociate with the negative samples. Okay, so far the techniques that we have seen, the skipgram model or the continuous bag of words model, the one problem was the efficiency, that we're doing multiple runs over our entire vocabulary or negative samples, whatever. But Glove is an alternative method of obtaining the word embeddings. The main improvement is that instead of doing multiple runs, we just do one pass over our vocabulary, and we generate what we call a co-occurrence matrix. So the co-occurrence matrix, which is shown over here, it essentially says that within a context window, let's say of 10 words, what are the number of times these words are appear together? So for example, like the word enjoy appears once with I and appears one with flying in maybe like context windows of like any sentences or context windows of 10 words. And likewise, all the other words. So this is the idea of the co-occurrence matrix. And the advantage is, again, that you just have to do it like one pass over the vocabulary, like the entire set or your training corpus or whatever. You can just generate it once. You don't have to do multiple passes. Now, how does it help us? So this is best elucidated using maybe a simple example. So if we look at the idea is that the ratio of probabilities of these words using the co-occurrence matrix provides us semantic similarity information. So how does it work? So we have ice and steam as our target words, and then we'll pick some k random words from the vocabulary. So here we have k as solid, gas, water, and fashion. And we are trying to infer some kind of semantic information using the co-occurrence matrix. So first we calculate, let's say our k is solid in this column. We get the probability of k given ice, which is just a number, k given steam. And then, so if there are any similarities, so then we calculate the ratio of these two probabilities in the bottommost row, k given ice over k given steam. So if you consider this, like if k equals to solid given ice should have a higher probability than, let's say, solid given steam. Do we agree? Because ice is solid, yeah. So if we do the ratio, we expect this ratio to be high. Now, what if k equals to gas? Gas given ice over gas given steam is going to be a very low number because gas is like related to steam. And if we look at the values of the bottom row, we can see that the first, when k is solid, ice solid, it gives us a high number. And for gas, it gives us a low number. And for unrelated words like water or fashion, it's basically 1 or close to 1. It doesn't convey any information. It's uniform. Okay, so this is on an illustration of how we can use GLOVE to capture semantic similarities between different words. This slide is actually a side. This won't be tested. It basically shows the objective function for training GLOVE model. The main idea is that you have a damping function or a weighting function f, and xij is your co-occurrence matrix. The intuition is that you want to have, you don't want to overweight for highly occurring co-occurrences, and you don't want to underweight for rare occurrence of co-occurrences. So this smoothing factor, essentially, this weights it accordingly, so it makes it smooth for high occurring co-occurrences versus rare word co-occurrences. That's it. That's the intuition. This slide is on evaluation. So the next question becomes that, okay, so we looked into different kinds of word embeddings. Continuous bag of words, skipgrams, and now GLOVE. But how do we know which one is better? How do we evaluate them? So for a period of time, the evaluation was sort of intrinsic, like each paper offered their own ways of showing how it's good, and sometimes it would be just cherry-picked nearest neighbor examples that match expectation. But over time, as NLP research has evolved, like now we have a very standardized set of tests. So the tests are, you're given your word embeddings, you test it against some standardized downstream tasks like sentiment analysis or named entity recognition, a whole bunch of NLP tasks. And they are, if you're interested, you can look at the website. So initially GLUE were released. GLUE were a set of standardized benchmark tests. And then when language models essentially solved those problems, they came up with SuperGLUE, which is a bunch of harder tests. And I think they're also almost solved now. But yeah, the point is that now everything is very standardized, and you can actually objectively compare different embeddings. So what this word embeddings can do? Yes, question?
So on the previous example so far, we have been looking at sliding window of size 2, because of which we have a matrix that is 2-dimensional. If we were to go into like 3-dimensional, like sliding window of size 3, would we got a 3-dimensional answer for that, or would we still use a 2-dimensional matrix and compare similarities?
So, yeah, but what do you mean by 3-dimensional window? Like it'd be a convolution then in that case, but yeah, so go on.
So like we're using co-occurrence matrix to
check
the number of times these words appear together. Right?
Okay.
So if the sliding window was of size not 2 but 3, like we were to check how many times these 3 words appear together.
I see.
Would we use a 3-dimensional matrix?
You could use it. I mean, you have to then you also have to just basically run tests and show that what is like whether it actually provides or captures any because the whole purpose is to capture semantic similarities. How if it helps, then yeah, you could do that.
Is that much of practically applicable, given that to make the algorithm more complex, or are there like better algorithms to
Well, we'll discuss this in later parts, but I think that has been mostly supplanted by what you call deep contextualized word embeddings. And the idea is maybe you're thinking like, what if 3 words? So yeah, we'll look into where instead of 3 words, what if we take an embedding of like, where right now we're doing what you call it a language model, like given a token, what is the current word? Given 2 words, what is the current word? So that's language modeling. So we're doing this forward pass. What if we have a representation that goes backward? And then you can take the forward pass representation, you can take the backward pass representation, take average of it, or concatenate them and train based on that. Will that help us better with, downstream tasks? The answer is yes, and we'll look into it. Like that's what we call deep contextualized word embeddings, like models following Elmo in 2018. That's what's been happening. Like Glove is not used in practice anymore. This is mostly pedagogical at this point. But yes, the answer is yes, and we'll look into it later. Yeah. Okay, so the linguistic regularities in vector space shows fascinating regularities. In this diagram, you can see, I think this is now, like you may have already seen this, that the regularity between countries and on the left-hand side and the capitals, and you see the regularity over here. Similarly, you can see this also holds for verbs and their comparative and superlative representation. So slow, slower, slowest, and then strong, stronger, strongest. So they maintain the same kind of pattern. So, and this is really fascinating because they also hold against semantic arithmetic operations. So if you do Paris minus France plus Italy, the nearest token is Rome, which holds in this embedding space. And other patterns that holds or we see in the latent space include analogies like pluralities of objects, superordinate word relationship. For example, shirt is to clothing and chair is to furniture. And the very famous queen minus king is equivalent to woman minus man. So this kind of similarities. This paper here sort of showed that what is something very intuitive, that your model will predict whatever you train it on. So this paper showed that if you train a model word embeddings, if you train word embeddings using in-domain data, then they're better able to predict in-domain similarities. So for example, they trained data using only medical journals and EHR and medical reports. And then they showed that embeddings trained only on medical records does a better job at capturing semantic similarities for medical terms as opposed to the same word embedding trained on generic data like Google News. So this raises an important question is that if that is the case, then what about the historical and societal biases that we have in generic data? Do language models or do word embeddings capture those in generic data? And as it turns out that it does. In this very famous or interesting paper, it showed that word embeddings trained on generic data shows patterns where man is to computer programmer has pattern similarity with woman is to homemaker. If you see in this picture over here, on the right-hand side, you have like the x-axis is sort of the gender axis, and the left-hand side is like she-specific words, right? And everything that is above the x-axis, this shows what should be gender-neutral words, but aren't. So here you can see that the words like homemaker is much closer to she as opposed to like brilliant, genius. They're much closer to he. So these inherent biases is a problem because these gender-neutral words, if you think about it, should actually lie like in the middle where it's not biased towards any gender. At the same time, there are certain analogies that are okay. So, for example, like she's to girlfriend and he's to boyfriend, it's an appropriate analogy. And even if there's gender bias to that word, it shouldn't matter. So this was shown on like word-to-vec embeddings trained on Google News, which is generic data. And you can also see some extreme examples here. The paper lists some of the associations, gender-based associations for what should be gender-neutral words. Yeah. So how do we solve this? This is a problem we should fix, and the solution is to essentially project the gender neutral words away from the gender subspace, gender definitional subspace. So over here, if you look at the red words, they are gender definitional, like he, she, queen, king, queen. And then you have the neutral words, which are in blue, like programmer, smart, or pink, or cute, homemaker, etc. So the solution is that we take the gender neutral words and we sort of project them away from the gender definitional words. So what we want to do is that somehow make all these blue words projections, maybe collapse them in the center so that they're equidistant from, like, the gender definitional words, so they're not related. And that's exactly what is done using hard debiasing. So after hard debiasing, they projected this, like the blue, the gender neutral words into an axis that is neutral to the gender definitional words. And how do you test this? You basically generate a bunch of analogies before debiasing and after debiasing, and you sort of see the results. So on the left-hand side, you can see that the green line shows, now it's red. The green line shows the hard debiasing. After debiasing, the analogy is generated, and the blue one shows before debiasing. And for stereotypical analogies, we see that it's depressed. That is what we want. However, also consider that there's certain words, as I said, that they're okay, they're appropriate analogies, like he's to brother, she's to sister, right? So we do another sort of set of appropriate analogies results, and they show that they're not suppressed, which is also what we want. Any questions? Okay. All right, so the last 10 minutes, I want to get started on the neural language models. And I will start with a simple pedagogical model. So up until now, the word embedding learning or word representation learning techniques that we've seen, it actually introduced the word prediction tasks. So you're given a word and you're trying to maximize, or you want to maximize the output word given this. So that's like a bigram distribution. Now, we want to extend this idea to more words. So now let's say we want to train what if a trigram model is essentially you're given what is the word given the last two words? And in the figure over here, what you see is that you take the last two words. So it could be we can start with the start of sentence token and I, the first word. And then you basically get the embedding for those two words and then propagate it up, and you get the probability for the second word. Okay? Let's say this is am. And then in the next iteration, you take am and you basically put I and am, and then you get a probability distribution for the third word. Okay? And you do that for all the words in the sentence except for the last word, because after last word, we don't have anything to predict. So in that way, so you have a probability distribution for the second word, third word, fourth word, and so on. And then you get the probability of the entire sentence by simply multiplying the probabilities for each of the words from the distribution. And that is the probability of a sentence. So yeah, so for illustration, here, so you have the two words, two writers, and then you get the next word as where, and then you basically feed forward that, writers where, and then you get the next word, and so on. So the training approach is simple. It could be a simple SGD-based training where you randomly choose a batch of training data, and then you propagate the words through the current model, get the word likelihoods, and you can calculate the loss because you know the ground truth answer and your predicted answer. And then you're going to backpropagate that loss, gradient step to update the model parameters, and so on. Okay, so what is the training objective? So from previous lecture, you know that what is a cross entropy loss, right? So you know that less cross entropy means, lower cross entropy means less uncertainty. So our goal is to have minimize cross entropy between our ground truth corpus and our model prediction. So given our corpus, we have our model prediction as PMC. So we want to minimize this. That is our objective function. And we can present this in a mathematical form over here, which is the mathematical expression for cross entropy. And C over here is just the normalizing factor for the number of words in the corpus. So minimizing this negative log likelihood is the same as maximizing the log likelihood of our model prediction. And then this is essentially, this simplifies to probability of a word in the corpus. How do we calculate the probability of word in the corpus? It is the same idea as the sentence. So you have a corpus like all the words, you just multiply the probabilities in order to get this probability of the corpus. So and this is this, And so this is our essentially loss function, and we do the same spiel where we take gradients and run the model, and that is how the training works. Here we can see that this is our objective function, and we'll be optimizing this objective function using gradient descent. So the advantage of this language models, it generalizes better than just maximum likelihood-based language models. We also have the advantage of the semantic information as conveyed in word-to-vec. The problem of training a model like this is the computation. It takes relatively long to train, and the number of parameters scale poorly with the increasing context. So because you see that the number of trigram expressions as we increase the sentence length will quickly multiply and become computationally infeasible. So usually our traditional data sets for neural language modeling, basically the idea is that they're large data sets, they have lots of tokens, and their vocabulary size are very large. And then the computational effort to train these models using this approach can be computationally infeasible. And then next we talk about how we can simplify and speed up this process. So there's few ways to do this. We can replace rare words with just one token, or we can subsample frequent words. But in terms of algorithmically, we can apply hierarchical softmax. There are a few other techniques like noise contrastive estimation and negative sampling, which we'll not talk about. We'll only illustrate hierarchical softmax today. So the idea of hierarchical softmax is essentially, you saw that before, the denominator was prohibitively expensive, where you had to go through all the words of the vocabulary. So now we're saying that we can make this a little bit better if we can break up or factorize this prohibitive denominator. The way we do this is by creating bins of words by the frequency of appearance. So now what we do is, given an input word, we first predict that, okay, so I have 10 bins. I've given a word, so which bin should I look for? And so we first predict that, and then after that, so if it's in bin number 2, then we just go to bin number 2, and we only bother ourselves with the number of words in the bin. And as you can imagine, that you can really, the number of words, if you bin it, it decreases significantly. So exactly this is what you're showing over here, that factorize this into, first you find the probability of the bin given the input word, and with that you find the probability of the output word given the input word and the bin. And the softmax basically simplifies to this two softmax operations, but of lower computational requirements, and that's why it's called hierarchical softmax. Okay, so we will start, we'll stop it here, and we can use the last 2 minutes as question answering. We'll start with recurrent neural networks on Monday. Thank you. Are there any questions? Yes.